Hi, I'm Cameron Gibelyou. As of fall 2011, I'm finishing up a PhD in physics at the University of Michigan in Ann Arbor. I do research in cosmology and astrophysics, and I've taught astronomy to college students, high school students, and junior high students. I've always loved learning about the world I live in, and that's part of what drew me to studying astronomy. It gives me the chance to learn about what the universe around us is like, and how small yet magnificent our own planet is. This is me near Mount Rainier in Washington State, where I grew up, and on the Great Wall of China. You can see that regardless of where I am, I like to advertise my baseball allegiances. I've joined up with the Big History Project to help give you an introduction to some of the challenging concepts related to cosmology and astronomy. If you're in a Big History course right now, you're exploring material that's very exciting to me, and I'm excited to help you learn about it. This first talk is about what happened 380,000 years after the Big Bang. This is an important time because it's when stable atoms appeared for the first time in the history of the universe. To understand why this is significant and why it happened when it did, remember that astronomers have observed that the universe has been expanding ever since its infancy. As it expanded, it cooled down, going from a very early time in which all the matter in the universe was packed together in an incredibly dense state, to later times when the matter grew less hot and dense. The left side of this image depicts the conditions in the universe earlier on, when it was hotter and denser, and the right side depicts the conditions later, when it was less hot and dense. The 380,000 year mark is in the middle. Before that 380,000 year mark, the universe was so hot that protons and electrons simply couldn't stay together. Anytime protons and electrons combined to form an atom, they just got split apart. This meant that there were a bunch of free protons and free electrons zooming around everywhere in the universe. Light scatters off free electrons, so at this early stage, light couldn't travel freely. Anywhere a photon went, it would run into an electron and scatter in a new direction. But as time went on, the universe expanded and cooled, and eventually it became cool enough for protons and electrons to stay together, forming stable atoms, both hydrogen and helium. This means that after 380,000 years after the Big Bang, not only does the universe have stable atoms in it, but light can now travel freely, because all those electrons that scattered the light before are no longer free, but are safely bound up in atoms. It's like going from an entire universe with dense fog — remember, you can't see through fog because it scatters light — to the fog suddenly clearing up, so that light is free to travel. So that's how we get the first atoms in the universe, and it's also when the universe becomes transparent, meaning light can travel freely through it, just like light can travel freely through a transparent window. You might ask how we can possibly know about all these events that happened so long ago. After all, this didn't happen in a galaxy far, far away. It happened before there were even any galaxies at all. So how do we know about it? As it turns out, we can directly detect the light that was around 380,000 years after the Big Bang. We call it the cosmic microwave background, or CMB. It's cosmic because it's everywhere in the universe, including where we are on Earth. And the microwave part is because most of the light is at microwave wavelengths, not too different from the microwaves in your kitchen microwave oven. And because it's been free to travel and has interacted with matter so little in the last 13.7 billion years, the cosmic microwave background still carries the imprint of what the universe was like in its early years. It's like a fingerprint that barely gets smudged in billions of years of cosmic history. This image, which represents observations made by NASA's Wilkinson Microwave Anisotropy Probe satellite, or WMAP for short, is like a picture of the universe in its infancy. The reason why it's oval-shaped is that it's a projection of the sky onto a two-dimensional surface. Just like you can project the surface of the Earth onto a flat surface, you can do the same with the sky. And that's what we've done with these observations of what our sky looks like when astronomical instruments observe microwave radiation rather than visible light. The colors indicate very tiny variations in the temperature of the CMB, which correspond to very tiny variations in the density of matter in the universe 380,000 years after the Big Bang. To get a sense of just how early in the universe's history 380,000 years after the Big Bang is, think about this. The present age of the universe is 13.7 billion years, and so 380,000 years is about 1/36,000th of its present age. If you're currently in high school, then when you were 1/36,000th of your current age, you were a few hours old. Why are we so confident that the CMB really is from the early universe? The answer to that question is a history lesson in itself. In the 1920s and 1930s, Edwin Hubble and others observed that the universe appeared to be expanding and cooling, suggesting that it was denser and hotter in the past. This led to predictions that there would be background radiation filling all of space, along with detailed models of what properties it would have. These predictions provided the opportunity to test the Big Bang model, and observations of the CMB made in the 1990s and 2000s, including the observations pictured here, provided spectacular confirmation of these predictions. In other words, theories of physics predict that the cosmic microwave background should have certain properties if the Big Bang is correct, and then when we observe the actual universe, we find that the CMB has exactly those properties. In particular, the CMB is observed to have what's called a black-body spectrum, which basically means that the properties of the light in the CMB are exactly what you would expect if the thing that emitted the light, in this case the universe itself, were nearly perfect at absorbing and emitting light. That's a key piece of evidence that the Big Bang, the idea that the universe started out very hot and dense and then expanded and cooled, is a good model of the history of our universe.